high. So this is now the next set of concepts that you need to understand. So after knowing how to interpret a potential energy diagram, now we're going to analyze further a real diagram with values of this potential energy. So if you look at closely the given diagram here, you see that the y-axis, of course, we know it's potential energy, and the unit here is expressed in kJ. kJ means that's in kilojoules. So these numbers should have a unit kilojoules. And of course, the x-axis is your reaction pathway. And the curve is here. So you see here the word reactants. So you have reactants A plus B, and then it goes up, then goes all the way down here to where the products are, and products are represented by C plus D. And if you look at the given reaction on top, the thermochemical reaction that we're given here is we have A plus B, which are your reactants, forming C plus D plus heat. So these are your products here of the forward reaction, because the arrow is going to the right. That's your forward reaction. And because you see another arrow going to the left, that's the reverse reaction in the process, in which the reaction goes to the left. So that arrow going to the left represents the reversal of the chemical reaction process. And so by looking at this curve here, we're going to answer 5 questions, and we have to make sure that we get all these answers correctly. Okay, so let's begin. The first question is, using the diagram above, determine what's the potential energy of the reactants, or the delta H of the reactants. Obviously, by looking at the graph, the arrow, the red line, represents the one from the X to where the reactants are. So that means, because this is where the starting point is, the reactants have a potential energy equivalent to where the line is, and that is equal to 350 kilojoules. So you don't need to have any calculation. It's just that by looking at the diagram, it says that the initial potential energy of your reactants is 350. Therefore, the answer is 350 kilo. Kilo is small letter K, and then joules, big J. So 350 kilojoules is the answer. The second question is, what's the potential energy of the products? So the products, obviously your products are on the right side of this forward reaction, and so the products potential energy after the reaction goes to this value here, which is 150 kilojoules. So the answer is just 150 kilojoules. And that is for the potential energy, or delta H, of the products. Number 3, what's the activation energy of the forward reaction, the EA of the forward reaction? So we know that activation energy is the amount, or the maximum area of the curve where you see your activated complex. And all you need to do is you look at the value of that maximum, which is 500, and then you know that it has ended in 150. So that means the total activation energy is subtracting your maximum. So your maximum is 500 kilojoules minus the final state of the products, which is 150 kilojoules. And so you will get the activation energy of this forward reaction from all the way here to where it is to be 350 kilojoules. So this is the minimum amount of energy so that the reaction will take place. So 350 kilojoules is the amount of activation energy. Again, how did we get it? You look at the maximum point of the curve, you read its value, subtract it with the minimum amount, which is actually just the potential energy of your products. So this is 500 minus 150, and so the difference is actually your activation energy, and that is 350 kilojoules in this case. Number 4, what's the total energy change of the reaction, which is the reaction, the forward reaction here. So the total energy change of the reaction is, remember the formula of the delta H of the reaction is always delta H of the products minus the delta H of your reactants. And we know that we were able to read the values of the delta H of the products and the reactants here. So delta H of the products is 150 kilojoules minus the delta H of the reactants, 350 kilojoules. So 150 minus 350 kilojoules, then your difference is negative 200 kilojoules. Negative 200 kilojoules gives you the value, which is this. This is the one in orange. Negative because the products is lower compared to the reactant's potential energy. So 150 minus 350 gives you negative 200. And again, to get the total energy change of the reaction, it's always the products minus reactants. And how do you get products and reactants? We got it from numbers 1 and 2, which is just taken from the diagram. And then in number 5, using the value that we get from number 4, we can now deduce and figure out if the reaction is endothermic or exothermic. Because the sign is negative, negative means that the energy lowers down because part of the energy were released into the surroundings. So therefore, the reaction is exothermic. And again, exothermic reaction will always gives you a negative value of delta H of the reaction. So take note, negative value of delta H of reaction gives you always an exothermic reaction. Okay, I want you, before you end this video, please make sure that you take notes of this on your notebook and you answer it on your own, and you can repeat it on your own so that the concepts will really be learned by you. Okay, so please look forward to the next set of video so that we can elaborate more on the concepts of potential energy diagram analysis. Thank you.